I expect for the 24 questions, probably 12 points apiece. So you can see an abundance of earnable extra credit is there. Go get it. Money in the bank. Now, which you began to discuss yesterday, our next general topic is that of determining hydronium ion concentration for water solutions of polyprotic Bronsted-Lowry acids and bases. In the acid-base table, which I expect by now you've recognized, there are the formulas for a few polyprotic Bronsted-Lowry acids and bases. But in the table, there's only one listed which is strong and molecular. This relates to the fact that there are three subcategories of Bronsted-Lowry polyprotic acids. I've classified these into the three different subcategories because the chemistry of these three systems is distinctly unique and not like any of the other systems. The parent acid is strong and molecular. For example, the sulfuric acid molecule. We'll talk about such in a moment. The parent acid is weak and molecular, like dihydrogen sulfide or hydrated CO2, and a couple of other examples contained in the table, like the phosphoric acid molecule and oxalic acid, which I believe is written in our table as HOOCCOOH, something like that. Condensed formula is H2C2O4. Many of you discussed analysis of solution properties for weak molecular polyprotic acids yesterday. We'll expand on such as our conversation proceeds today. And then at last, the polyprotic acid is a hydrated metal ion, like this. As we shall see, this is the most challenging case by far of these three different types of polyprotic Bronsted-Lowry acids. This is the most difficult. This leads to the most difficult solution calculation for solution hydronium ion concentration. That's why we shall discuss this one at the tail end of this. And that'll not be part of this exam. I doubt that we'll even get to that today. So, we'll start with this. 1,000th molar sulfuric acid solution. As you know, I should think if you know anything, you know this. If you're going to deal with the chemistry of a system, you damn sure better be able to know what's in it. Which means from a qualitative standpoint, principal system inventory. From a quantitative standpoint, which this is, because we got to calculate hydronium ion concentration, quantitative principal system inventory. And how do we know how to inventory a system? We pay attention to the chemistry which occurs when the system in question was prepared. So in this case, what happened when the sulfuric acid solution was prepared? If we wish to consider this as two steps, sulfuric acid molecules added to the solution react with water, giving hydronium ion and hydrogen sulfate ion. Reaction extent is 100%. After which I've written so. What does that tell us? For this case, I'm in the lab. There's a flask with a stopper on it. contains a colorless liquid, and that's the label right here. Well, if this goes 100%, that means the hydronium ion concentration in the solution has got to be at least what? This. Can't be smaller than that, because this goes 100%. Now, will that be the solution hydronium ion concentration? In most cases, no. Because the conjugate base of the sulfuric acid molecule, specifically the hydrogen sulfate ion, is an interesting base in that in water solution it does not ever behave as a base. It behaves as an acid. You know that from examination of the acid-base table. Hydrogen sulfate ion is a base which is considerably weaker than water. But as an acid, it's considerably stronger than water. So even though this species is the conjugate base of the parent molecule, it behaves as an acid rather than as a base in water solution. Here's the reaction equation, which corresponds to what property of this acid? An acid is reacting with water to make hydronium ion in the conjugate base of the reacting acid. That means, by definition, the K value for this equation, reaction equation, is what? What? Ka of this stuff. And Ka for that stuff is 1.2 times 10 to the minus 2. Now, what have we learned about ionization extent? We learned that ionization extent depends on two factors. What are the two factors? Ka, how strong is the acid? This acid is pretty strong as far as weak acids are concerned. 1.2 times 10 to the minus 2 is a pretty big K value for a weak acid. And what else? The dilution factor, right? How concentrated is the solution? The lower the solution concentration, the more dilute solution, the greater the ionization extent. So here we got a Ka value which is rather substantial as far as weak acids go, and a fairly dilute solution. So what do you think is going to be the ionization extent for hydrogen sulfate ion in accord with reaction equation 2 for this solution? Large. That's a good bet. So that's going to tell us that the solution, the concentration of hydronium ion for this solution will compare how to m sub I? Greater than m sub I. What's the maximum possible value for hydronium ion concentration in this solution? Twice m sub I, when this too goes 100%. We're letting this stuff talk to us. That's what counts. If you understand the chemistry, the rest follows. If you don't understand the chemistry, then this is horribly painful and torture. Because you're looking around for equations or recipes to shove numbers in and stuff like that. That gets you nowhere here. That gets you nowhere in real chemistry. So, just to be sure you understand what we're going to next look at, which in fact we just discussed. We'll play a game. For some reason I've discovered this game seems to help students get the message for this system. Let's put over this stuff, never mind this for now. Let's put over sulfuric acid molecule 100. If sulfuric acid molecules start at 100, and this reaction goes 100%. After this reaction goes, how many of these we got left? How many of these we got? And how many of these we got? 100. How about that? Now then, we go to the second reaction. When we go to the second reaction, we know this starts out at 100. And this is going to wind up as at least 100. So we'll write 100 plus and 100 minus. Minus what and plus what? I'll put down question mark. The identifier of the great unknown. Question mark. What the hell is question mark in this system? What is it? I'm listening. Concentration of sulfate ion, absolutely. And once you see that, you really have done the chemistry for this system that you have to do in order to deal with analysis of the system. So in turn, this tells us the sulfuric acid concentration for the system is the label on the bottle plus the solution plus the sulfate ion molarity for the solution. The hydrogen sulfate ion concentration is the label on the bottle less the sulfate ion concentration. And if I add the sulfate ion concentration to the hydrogen sulfate ion concentration, put brackets around this, what do I get? For this example system, what will I get? If I add the concentration of sulfate ion to the concentration of hydrogen sulfate ion, what must I get? For this system. I want to know the number. What will I get? 100. I started with 100 of these, and some of them became this. So, if this goes 50%, this will be 50 and this will be 50. If this goes 40%, then this is 60 and this is 40. If this goes 30%, this is 70 and this is 30. Whatever. So the molarity of this plus the molarity of this is always m sub I. We're letting this talk to us. Then we got it made. So that's what I've written here, which we have just discussed. We've recognized that hydronium ion molarity must be at least m sub I, but it's a good bet it's bigger than m sub I. And the hydronium ion molarity is, for the solution, m sub I plus the sulfate ion molarity, while the m sub I value is the sum of these two concentrations, which we just discussed. So if I take what I have here and combine them, I find that the hydronium ion concentration for each and every sulfuric acid solution is the hydrogen sulfate ion molarity plus twice the sulfate ion molarity. And a lot of times when I write this stuff, at least when I write this stuff the first time, many students look at this and go, ah! Yet if I put up X's and Y's, you'll be doing fine. But the hell with X's and Y's. I want to know what I'm dealing with here. I'm not dealing with X and Y. I'm dealing with hydronium ion concentrations and sulfate ion concentrations and hydrogen sulfate ion concentrations and numerical label on the bottle for the concentration of the solution containing such. I think something just passed away. Who cares? I can boom. So for this particular solution, here's the Ka expression. And I've made the substitutions in accord with what we have now learned about this solution. 1.2 times 10 to the minus 2 is equal to this. So you got one unknown. As we have written it, the unknown is the sulfate ion molarity. How are we going to solve it? Well, you know I'm not solving it with any kind of rigorous algebra or quadratic recipes or stuff like that. I'm solving it as we have already programmed you to solve such, by speculation on percent ionization, or if you prefer to call it ionization extent, who cares? And what ionization extent have we said you should always try first? 50%. Because 50% is half of m sub I. And now the arithmetic couldn't be simpler. What's half of this? So if I try 50%, what does this term equal right here? What does this term equal at 50% ionization? 1.5 times 10 to the minus 3. Half of this added to this. That's it. Because at 50%, these go out. That's the simplifying part, right? I don't care what m sub I is. I don't care. This is always true at 50% ionization. Now, how does 1.5 times 10 to the minus 3 compare to Ka? It is a good deal smaller, isn't it? So with this one test, I now know, and it follows from the conversation we had earlier. Ka is rather large as far as weak acids go, and m sub I is rather small. Both of these support the conclusion, before we even did any arithmetic, that the ionization extent of reaction 2 is substantial. And we've now determined that it compares how to 50%. It's bigger than 50%. So you know how to play the game. That's all that matters. What would you like to try next? Pick an easy number.
5%.
Well, 75% might require me to do a little bit more arithmetic thinking than I feel like doing right at the moment. So I'm going to try 80%. Now watch out, because I have to do this horribly challenging arithmetic of taking 80% of this value. What is 80% of this value? Zero point zero 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 8. So I will have 0.0018 times 0.0008 divided by what? 0.0002. Now watch out, here comes the next challenge. 0.0008 divided by 0.0002. What's that equal to? 4. Boy, that was hard. And if you take stuff like this and start shoving it into that damn thing with buttons on it, something's wrong. Do I sound sharp and clear and emphatic about this? This is the computer you want to use. This is the best one you got by far. Put that push button thing to shame, provided that you use it. So comes the next part. 4 times 0.0018. 0.0072. How does that compare to Ka?
Smaller.
It's still smaller, isn't it? Ha ha! So we recognize that the ionization extent is surely substantial for this. I think it comes out to be 86 or 87%, something like that. Let me take a peek. The 2 sig figs (87% is correct. You'll do the arithmetic as necessary to convince yourself, if you're not convinced. All right? Now then. There I saved all this space because I was going to write all this down. And I said, to hell with it, I'm going to write it down. Who cares? Now let's talk somewhat further about sulfuric acid solutions. What can we say about system species concentrations if we are dealing with extremely concentrated sulfuric acid solution? I'll write this up here. First of all, for such a solution, is the pH guaranteed to be quite low? Well, yes. A very concentrated sulfuric acid solution, you've got to have a very high hydronium ion concentration. Next question. For this kind of solution, how will the hydronium ion concentration compare to M sub I? You expect them to be pretty near equal, or perhaps in fact equal? Or do you expect the hydronium ion concentration to be still substantially greater than the M sub I value? About equal or considerably greater? What do you think? About equal or considerably greater? If I have a very concentrated sulfuric acid solution, what's the ionization extent of reaction 2? Damn small, isn't it? That's all I need to know. So the hydronium ion concentration and M sub I value are going to be close to each other, perhaps equal. How will the hydronium ion concentration compare to the sulfate ion concentration for a very concentrated sulfuric acid solution? How must the hydronium ion concentration compare to the sulfate ion concentration? Similar, double, triple, or a hell of a lot larger? Which of these you want to vote for? You want to vote for a hell of a lot larger? You're damn right. There's a second ionization reaction, which is the only way you get sulfate ion in here. Ain't going anyplace, practically speaking. And it's a very concentrated solution, so M sub I is a big number. Sit down, for example, and calculate the sulfate ion concentration for 6 molar sulfuric acid solution. Now you know how to do it. And you'll find out that for quite a concentrated sulfuric acid solution, like 6 molar, where the hydronium ion concentration will be 6 molar, that the sulfate ion concentration is a lot smaller than 6 molar. What is the sulfate ion concentration? What is it? And now I'm not asking for a comparison. I want the answer. Tell me the answer. Tell me the value for the sulfate ion concentration in quite concentrated sulfuric acid solution.
Practically 0.
I heard a vote for practically 0. I do not accept that vote, but at least I got a vote. If I have a very concentrated sulfuric acid solution, then the hydronium ion concentration is in essence M sub I. What will the hydrogen sulfate ion concentration be? In essence, M sub I, because this isn't going anyplace. So there's your sulfate ion concentration right there. How about that? You think about these solutions, the chemistry falls apart, if you think the chemistry. Isn't that interesting? Isn't that interesting? Now I'll ask another dirty question. For sulfuric acid solutions, where the second ionization reaction goes to a measurable extent. Okay? For a sulfuric acid solution where the second ionization reaction goes to a measurable extent, how will the sulfate ion concentration compare to 1.2 times 10 to minus 2? It'll be either equal to 1.2 times 10 to minus 2, bigger than 1.2 times 10 to minus 2, or smaller than 1.2 times 10 to minus 2. There ain't no other possibilities. Are you really telling me that when I get a less concentrated solution, I'm going to get more of something? How about that? Dirty, isn't it? Here we have a much less concentrated sulfuric acid solution. Right? The 1,000th molar? You think the sulfate ion concentration in here is bigger than 1.2 times 10 to minus 2? Because if it is, that term in the denominator is negative. You see that? 0.0010 less 1.2 times 10 to minus 2 is negative, and that ain't possible. You can't have negative concentrations. You got to let this stuff talk to you. And then it'll make sense. Hey, these are nasty questions I asked. I know that. I've asked questions just like I just discussed with you many times in the past. Particularly when I've taught this in the summer when I can give real exams. But now that's even been taken away. Now when I do this in the summer, I'm still going to have to use this multiple choice trash format. But we'll survive. See, when I give you questions where you have to answer by writing stuff down on a piece of paper, so I find out what you're thinking, then I can identify the difficulties in my presentation and what you don't know. But if what you do is bubble in a circle on the answer sheet, I don't know what the hell's going on. I'm no crystal ball reader. I can't read your mind. One of these days, universities will learn that multiple choice exams ought to be condemned and banned and outlawed. Then we'll make a big step regarding educational progress. Interesting, isn't it? And it's so obvious. So obvious.
Would you rather than ban calculators or multiple choice exams?
Oh, I won't ban calculators because I will have asked you to prove to me at the start of the term that you can use the calculator, which means you're going to prove that you can do arithmetic. Because if you can't pass that test, I don't let you in the course. Yeah, I got ways around it. But I'm for educational advancement. That's what I want. And you folks can do this. I know damn well you can do this. Nothing wrong with your intelligence. What's wrong is that it hasn't been programmed properly. And that's not your fault. Well, I'm here to do what I can to change that. I think you know that by now. All right? So the hydronium ion molarity is going to be a hell of a lot bigger than the sulfate ion molarity. The sulfate ion molarity will be 1.2 times 10 to minus 2. And the hydronium ion molarity, like the hydrogen sulfate ion molarity, will be equal and be equal to m sub I for the very concentrated solution. See? All that follows from this chemistry. Now what about the very dilute solution? Well, this is pretty dilute. Well, for the very dilute solution, how will the hydronium ion molarity compare to the sulfate ion molarity? The answer's on the board. I want to know specifically, for the very dilute solution, how the hydronium ion molarity compares to the sulfate ion molarity. I heard it. Double! The first reaction goes 100%, and now the second reaction is practically speaking going 100%. Right? 2. Hot chalk. Double. Okay? But the hydronium ion concentration will be quite small. And relative to the very concentrated solution, the pH will be much higher. That's all. What will this molarity be in the very dilute solution? Practically nothing. This has all gone away. Became this. And hydronium ion. All right? A practical example. As it follows from what we've done. Question 1849. Let's stipulate that we're dealing with a sulfuric acid solution where the hydronium ion molarity is 4 times the sulfate ion molarity. Can we get the hydronium ion concentration for the solution? Or the sulfate ion concentration? Or the hydrogen sulfate ion concentration? Or calculate M sub I? Who cares? We can do every one of these things. They're all the same question. Let's start with this. M sub I, CT for compared to sulfate ion in this system. What equivalency can we write regarding the label on the bottle, M sub I, and the sulfate ion molarity?
You can relate both of those to...
Well, I want to know the answer. How does this M sub I value relate to the sulfate ion concentration if it is stipulated that the hydronium ion molarity is 4 times the sulfate ion molarity? How does M sub I relate to the sulfate ion molarity if that condition be true? I'll write it on the board. See if you recognize such. Is okay, or are you mystified?
How does it equal 3?
What else could it equal? If the hydronium ion concentration is 4 times the sulfate ion concentration, M sub I has got to be 3 times the sulfate ion concentration. Got to be. You don't believe me? Let's look at these relationships. Okay so far? What did I say this is? 4 times the sulfate ion molarity, didn't I? Let's get this out of the way. Now watch out, this is tough. M sub I plus sulfate equals 4 sulfates. So if I subtract sulfate from each side, what the hell do I get? I know what's got you baffled, and I'm sympathetic with this. What's got you baffled is this funny formula, and this funny formula, and this funny formula. If I put in here A's and B's or X's and Y's, you'll zip through this. But as soon as I put in the chemistry, people get mortified. Don't get mortified. But that's the way life is. I'll tell you a story, because I like to tell stories. In high school algebra, Toledo, Morrison, R. Waite. Year 1956. There I am. In high school algebra class. My class was doing pretty good, but the class which followed my class, in the classes taught by the teacher who did algebra, who was a good teacher, in my estimation, Miss Baumgartner. Okay? She gave us a test, and just like the textbook, just like she had done throughout the term, all the unknowns were represented by X and Y. She gave the next class the exact same test, except she changed every X to an A and every Y to a B. And until that time, they had been outperforming us. They cold flat flunked that test. Now, she did this because she read something about it in some analysis of education processes or whatever. It's the familiarity thing. And she was astounded. She says, what went wrong? And you know what they told her? We know X and Y. We don't know A and B. Pick. That's the way the human person reacts when he or she sees something that he hadn't seen before. That's why the sulfate ion molarity and hydronium ion molarity baffle you. But this is why I tell you, don't take this stuff and start substituting X is this and Y is that, because you're going to you're going to lose the chemistry. And once you lose the chemistry, you lost the game in here. That's it, all gone. So don't do that. Hey, when you get practice at it, then do it. I don't care. I do it myself. You know, I'm writing out a long problem. I don't want to keep writing sulfate ion all over the place. So I'll write down X. But that's me. You're not permitted to do that. Remember me, I'm this pervasive ethereal spirit that hovers about you when you're doing this stuff with my club. X square! No X! Sulfate ion concentration. Now you know what to do with this. You'll find out also for this, hydronium ion concentration equals 2 Ka, which means it's equal to 2.4 times 10 to the minus 2. But you do it. That's what matters. Not hard. You now know what you need to know to wrestle with this.
Multiply by 2.
Now then, a couple comments on the water solutions of polyprotic acids for which the parent acid is weak and molecular. Okay? Statement. Now don't jump up and run away. The stuff on the weak polyprotics is not on tomorrow's exam. The sulfuric acid stuff we just talked about is. Okay? But let's take advantage of the 5 minutes we have remaining. Because this is where we're going to be going into and finish it up on Friday. And then we'll get into the real fun stuff about the polyprotic hydrated metal ion acids. That's where the fun really starts. Okay? If you have been doing what I have commanded you to do, that's what we want. You have read, because it's right there in the area of the notes which we are now considering regarding water solutions of polyprotic acids. That true carbonic acid is a much stronger acid than hydrated CO2. But what you've also read is when I make seltzer water. You familiar with seltzer water? Take water and bubble CO2 through it, that's all. You want to give it a little taste, you put in a little sodium bicarb, and then you call it club soda. I like club soda. Goes good with my vodka. Goes good with my bourbon. Man, I like club soda just to drink. So does my sweet little wife. She likes club soda mixed up with grape juice and Gatorade. Hey, she likes it. Nothing else matters. Once wife likes, that's it. Okay? But she's a darling. I like that too. I like a little bit low on the grape juice, high on the club soda and the Gatorade. Okay? When you put the CO2 in the water and make seltzer water or club soda, or by natural fermentation you make beer, whatever. You'll wind up with a system that's practically entirely hydrated CO2 rather than true carbonic acid. But studies have been done on true carbonic acid so as to find out that true carbonic acid is an acid which is, it's at least 100 times, I think about 1,000 times stronger than H2CO3. The data's in the notes. Okay? So let's imagine I figured out a way how to stabilize this stuff, because therein lies the problem. This is not stable, this is not stable. But this is more stable than this, provided the molarity of this is low. But you can't hardly make club soda at a concentration, I think about 0.02 molar is about it. 200ths molar. This is CO2, as we know. It's not polar, not very soluble in water. Now you can force a bunch of it into water under pressure and make a more concentrated hydrated CO2 solution. But you know, once you take the cap off, out it comes until you get an equilibrium molarity. In this solution versus this solution. How do these molarities compare? Given that Ka for this is a heck of a lot bigger than Ka for this. So this is bicarb in this solution versus bicarb in this solution. How will these molarities compare? In which solution will the bicarb molarity be greater? In this one, because the Ka value is a lot larger. Now comes the fun question, which some of you should know about because I think some of you got to this yesterday. How do these molarities compare in these two solutions? They're equal. They're equal. They're the same. Not only are these molarities the same, they're each equal to this value. How about that? Well, before we go further with what you are probably at present viewing as witchcraft, we'll leave this alone until next time.